Hello, my name is Andrei, and today I'm going to tell you about two different approaches of managing Kubernetes clusters, about the Openstack Magnum and about the cluster API. But before that, let me introduce myself and introduce my company. So, name's Andrei Novoselov, I work at the Gcore company, and I'm a system engineer team lead. Gcore has a lots of products, such as CDN, DNS, cloud, and a lot more. But I work at the Gcore Cloud, so I'll tell you about the Gcore Cloud. We have more than 20 locations around the globe where we are providing the public cloud service. So users can use some basic cloud services such as virtual machines, load balancers, bare metal servers, and firewalls, or more complicated platform services such as managed Kubernetes as a service, function as a service, logging as a service. Basically, anything as a service is in my team's responsibility zone. But today we'll talk about the managed Kubernetes as a service and about the Openstack Magnum and the cluster API. And we'll start with Openstack Magnum. So what does Magnum do? It orchestrates container clusters and it supports two technologies, Docker Swarm and Kubernetes, and we'll talk about Kubernetes. But Magnum itself cannot configure the virtual machines, and it uses another OpenStack component, which is called OpenStack Heat, and Heat creates cloud init config for the Kubernetes nodes, and it also updates application versions and configuration on the Kubernetes node. So let's take a look at the Magnum architecture. First of all, Magnum has an API, and it's an HTTP API. It gets some requests, and basically all those requests are some tasks. And tasks, for example, create a cluster, update the cluster, delete the cluster. So Magnum API puts those tasks into the RabbitMQ, and the Magnum conductor gets those tasks from the RabbitMQ and makes them done. And it's a pretty common architecture for the OpenStack service. So an API, RabbitMQ, and some engine. And Heat is pretty same. It also has Heat API, RabbitMQ to handle the tasks from the API to the engine and Heat engine. It also has a Heat agent. Heat agent runs on every virtual machine configured with Heat, and it updates the application version and application configuration if needed. So what's the limitations of this approach? Well, first of all, there is no control plane isolation from the user. So the user gets the full admin access to the Kubernetes cluster, and he can do whatever he wants with the control plane components, and that's not how you do the managed Kubernetes service. And there's one more minor thing. It's an OpenStack API, and we are not providing users access to the OpenStack API, so we have to hide this API behind the Gcore Cloud API. But it's not a big deal. Let's talk about the control plane isolation. Here's a scheme of Gcore Magnum-based managed Kubernetes service architecture on the cluster level. So managed Kubernetes cluster is always inside the client private network, and client can select which networks he prefers. And let's talk about the control plane. Control plane is 3 virtual machines, and on every virtual machines we have all the control plane components, Kubernetes control plane components such as etcd, Kubernetes API, control managers, scheduler, kube DNS, and so on and so forth. All of them are Podman containers controlled by the systemd. etcd, kube DNS, and control and kube API have their ports exposed outside of these virtual machines, and we have load balancers. So there's 3 virtual machines, 3 etcd, replica, 3 kube APIs, and we have cloud load balancers to hide all these replicas behind the load balancers. And we also have a firewall which only allows access to those 3 exposed services. And none of that is visible for the client. So client cannot see the firewall, the control plane nodes, and the load balancers. Client can have as much worker nodes as he wants, and on the worker node, kubelet is also inside the podman container, which is controlled by the systemd. And for the Kubernetes workload, the container engine is Docker itself. And if kubelet or any other pod inside the Kubernetes need to access kube API, etcd, or kubedns, well, we have to go through the cloud load balancers and through the firewall inside the master nodes, inside the control plane nodes. And that's it. And what's the pros and cons of Openstack Magnum? Well, the big plus is that it is OpenStack, and it has a great community which is developing Magnum and supports it and adds new features and fixes bugs for us. And I guess that's it. That's the biggest plus. And let's take a look at the downsides. Well, first of all, it is extra RPS for the Cloud API. Like I said, we had to hide the Magnum behind and the Heat APIs behind the Cloud API. So now all the requests to those APIs go through the Cloud API. And that's a lot of requests if you have a lot of clusters. But that's not a big deal. Well, the second thing is that this construction is really fragile. So what I mean, if something went wrong while the cluster was creating or updating, the Magnum cluster goes to the error state. And there is no way using the OpenStack CLI to make it alive again. So basically the debug looks like this. And you have to find the reason. For example, OpenStack could not create a load balancer for the etcd or for the Cloud API while it was creating the cluster. So cluster went to the failed state while it was creating. So let's say you fix it, the original reason. I don't know, you started the Octavia, maybe the problem was in the RabbitMQ, but now it's fixed and the load balancer can be created. And now you have to log into the production MariaDB and update some rows for this cluster and set like now this cluster is active, not in an error state. And the same for the heat. And if it's just one line for the cluster inside the MagnumDB, the heat has a little complicated structure of heat templates and heat stacks, and you have to find the file stack and update it. Well, and it's a lot of update operations on the production database, which is not what you want to do on a daily basis. And like I said, if Octavia was in some error state or maybe RabbitMQ, it happens from time to time. So you have to not only to fix that OpenStack component, but also to fix the Magnum clusters if they were creating while Octavia or Rabbit were not available. The other thing is observability. So let's say you want to know the state of all the Kube API containers in all your clusters. Well, you have to log in via SSH to the control plane nodes and to find out is there everything okay or not. Or you may create an Prometheus exporter if you're using Prometheus to monitor all the clusters, or do something with it. But from the box, there's no such thing as health check for all the systemd units on the master cluster. And if you want to be sure that everything is okay, you have to log in via SSH to those nodes. And there is no bare metal nodes, and that's a huge minus. And one more thing. Here's the compatibility matrix. On the left column, you can see the OpenStack version. and on the second column you can see the supported Kubernetes version. So if you are using Yoga, which is just 1 year old, the highest Kubernetes version for you is 1.23. And here's the Kubernetes supported versions for now. And it starts with 1.24 and 1.25 and 1.26 is the highest version. But in April we'll have a release, I hope, and this will change, and the supported versions will be 1.25, 1.26 and 1.27. So the OpenStack is about 2 Kubernetes versions behind the Kubernetes. So I guess it's a big deal, and we did not wish to support to add support to those Kubernetes versions to the Magnum, and we decided to take a look at other tools for managing the lifecycle of the Kubernetes cluster, and there's a project which is called Cluster API, and it's a Kubernetes project. And what's the goal of this project? Well, first of all, it manages the lifecycle, and by that I mean create, scale, upgrade, and destroy all the Kubernetes cluster using a declarative API. It works in different environments, both on premises and in the cloud, and it defines common operations and provides the default implementations and provides the ability to swap out implementations for the alternative ones. So if you don't like it, if you don't like something in Cluster API, you can do it your way. And Cluster API can be extended to support any infrastructure. And sounds great. So what is it made of? What are the main components of the Cluster API? Well, first of all, it's a controller manager, a bootstrap controller manager, control plane controller manager, and infrastructure provider. Let's talk about it a little. So Cluster API, basically it's 4 Kubernetes controllers. So it runs inside the Kubernetes. So you need a Kubernetes cluster to create another Kubernetes cluster. And it operates with the Kubernetes objects, with the custom resources. So these controllers, they control those custom resources and reconcile them. And what do we have out of the box? Bootstrap control out of the box supports kubeadm, microK8s, tailors, and EKS. Control plane control out of the box supports kubeadm, microK8s, tailors, and the project called Nested. And there's a bunch of infrastructure controllers for AWS, Azure, vSphere, Metal-free, well, lot of providers, but there is no jQuery provider yet. So let's talk a little bit more about how it works. So we have those binaries like controller manager, bootstrap controller manager, and control plane controller manager. They handle the whole life cycle of the Kubernetes cluster, and they know nothing about the infrastructure behind them. So that's why you need an infrastructure provider. Infrastructure provider is a thing that allows Cluster API to create some basic infrastructure objects such as load balancers, virtual machines, firewalls, server groups, etc., etc. And the Cluster API says, okay, if your infrastructure provider allows me to create virtual machines, load balancers, and firewall, then I can do anything on that cloud. So let's take a look at some YAML. And let's take a look at the cluster object. And there's obviously some cluster configuration inside the spec, but I wanted to point your attention at the control plane ref and infrastructure ref. So we have a cluster, and it has infrastructure reference to the gcore cluster object, which is the implementation of this specific cluster on the gcore provider. And if we take a look at the control plane, we'll see pretty same thing. It says, okay, we need 3 replicas of control plane nodes with some Kubernetes version, and it has a reference to the infrastructure provider, to the kind gcore machine template. So we have a template for the gcore specific infrastructure provider for the machine to create a control plane node, and we need 3 of them. So control plane has a reference to the gcore machine template on the infrastructure, and the same for the machine deployment. Machine deployment is an object which describes the worker group of some Kubernetes cluster. So this one says, okay, we need 6 workers, and to create them, please use the infrastructure reference to the gcore machine with this name, and that's it. So what I tried to say, that this is how Cluster API works. It has some basic objects which do not change from one cloud provider to another, and the cloud provider will always give an infrastructure reference. The infrastructure provider, my bad. So cluster is always referred to the gcore cluster, control plane, and machine deployment. Both are created from the gcore machine templates. And one more thing, meshing. Meshing is an object which describes a control plane node or virtual machine or worker virtual machine or bare metal machine. So what are the limitations of the cluster API out of the box? We have kubeadm bootstrap provider, which is more or less suitable for us. kubeadm control plane provider. So that basically means that the kubeadm will be used to bootstrap the control plane and to join workers to that control plane. And as a provider for the cluster API, which uses kubeadm. And there is no infrastructure provider for the gcore infrastructure. And what else limitations can we see? There's also no control plane isolation from the user. You need a Kubernetes cluster to create another Kubernetes cluster, and there is no gcore provider. And we still have 3 virtual machines for the control plane if we use kubeadm. So we decided to do it our way, and this is our implementation of the cluster API. We decided not to use 3 virtual machines for the control plane. We already have a Kubernetes cluster to handle cluster API, and we decided to put the control plane containers into the cluster as well. So we have a namespace for each client cluster, where we have some custom resources describing cluster, gcore cluster, some control plane, some machine deployments. And we also have the control plane pods inside it. So the control plane components are pods inside the service Kubernetes cluster. And all the cluster API objects are at the same namespace as the control plane pods. And we have no virtual machines for the control plane. And so to do that, we had to create gcore bootstrap controller, gcore control plane controller, and infrastructure provider, which is called capgc. And thanks for our colleagues from the Wargaming for help with that. Thank you, guys. And we had to do 2 more things. We had to create OpenVPN controller, and we use Argo CD, and we'll talk about it a little bit later. So let's take a look at the gcore cluster API-based managed K8s service architecture. So now you can see that there are some differences. In client private network, there's no master nodes anymore, only worker nodes. And in gcore private network, we have a GCore service Kubernetes cluster where in some namespace we keep all the custom resources of the cluster API, such as, like I said, cluster, machine deployment, control plane, and so on. And also we have control plane binaries such as etcd, kube API, controller manager, scheduler, and some more. So, because of the service cluster is in some GCore private network, and the worker nodes are in the client's private network, there's no network connectivity. So, what did we do? We used a cloud load balancer to expose the kube API to the public IP address. So all the components on the worker nodes can access the kube API via the internet. And that's it. That's simple. But what about the reverse connectivity? What if someone would like to do to type the command kubectl logs? And what happens when you do that? Your Kubernetes API works as proxy to the kubelet and shows the log from the kubelet. So kubelet can get the logs from the node. What if someone would like to use a port forward? It's pretty same. Kube API works as the proxy to some service in the Kubernetes. And Kube API has no way to access the kubelet because the kubelet is inside the client private network and is not accessible directly. So, and the admission webhooks. So what if Kube API would have to validate some custom resource before putting it to the etcd? It will need to access some pod inside the client clusters, and there's no way to do it. So VPN. We decided to do it this way. On the client side, we put a pod with OpenVPN server, and we expose it with a cloud load balancer to the internet. In the control plane, in Kube API pod, there are two containers. One of them is Kube API, and the other one is the OpenVPN client. And the OpenVPN client connects to the OpenVPN server pod through the cloud load balancer, and it gets the routes to the node network, pod network, and service network. And now, right inside the pod of the Kube API, we have some routes to all those networks, and Kube API can access kubelets on the node network, services, and pods inside the Kubernetes cluster. But what if client deletes something? What if client deletes an OpenVPN server, Calico, kube proxy, and we have an Argo CD for that? So inside our service cluster, we have an Argo CD, which have apps for all infrastructure, which should be controlled by GCore inside the client's worker nodes, such as kube proxy, kube DNS, Calico, and OpenVPN service for the reverse connectivity. So Argo CD renders the manifests for all that infrastructure and puts them directly into the Kube API, which is located inside the GCore service cluster. And then the kubelet accesses the Kube API and finds out what pods should be run on the node. So if clients deletes anything using the kubectl, the Argo CD will recreate it. And one more thing about the observability. So comparing to the Openstack Magnum, where we could not find any suitable tool to find out is everything okay with cluster, we have it just out of the box. So we can use a command like kubectl get cluster -a capital A, and we'll get all the clusters which were provisioned using the cluster API in our service cluster. So we can see that we have 1, 2, 3, 4 clusters, and all of them are ready, and their version is 1.24.10. We also can get information about all the control planes. So the output is pretty same, but it tells us everything about the control planes, not about all clusters. So we can see that all control planes are ready. So etcd, Kube API, Kube Scheduler, Controller Manager, all of them are up and running, and here's the version of the control plane. We also can take a look at the worker pools, which are called machine deployments in the cluster API, and we can see that in this namespace, the first one, there should be 3 replicas, so 3 worker nodes, and all 3 are ready and all 3 are updated, and they are running, and they're 2 days old, and the version is 1.24.10. And we can get information about any cluster we're interested just with single kubectl command, or about all of them. And we can get a machine. So kubectl get machine will minus capital A will bring us all the virtual machines or bare metal machines which are controlled by cluster API inside this cluster, and we even can see the OpenStack ID of these virtual machines and how long it exists and the Kubernetes version on it. So it's really great. And that's it. We moved from the cluster API to the Magnum, and what we got from it? We got a great speed up. All the control plane is just a bunch of pods, and it's really much easier to spin up some pods than to create a virtual machines. We got the easy updates, and that's much faster, obviously. We got the easy updates. We have 1.24, 1.25, and 1.26 version of the Kubernetes out of the box. And we can update all the infrastructure inside the client's cluster with our Argo CD applications. And it's really easy as well. We got the reconciliation loop. So if the heat tried to create, for example, a load balancer and failed, then you are the one who have to fix it. If cluster API tries to create a virtual machine or load balancer or whatever and fails, it just waits a little and tries again and tries again and tries again until everything is done well. And it's really great. So after you fixed your Octavia or Nova or RabbitMQ inside the OpenStack, you do not need to reconfigure all the cluster in the region. Cluster API will just do another try and succeed, and we'll be happy with that. We got the bare metal nodes with our powered by Intel, and it's a great feature, and a lot of our clients wanted bare metal worker nodes, and now we have it because we created an infrastructure provider which can use bare metal nodes as worker nodes for the Kubernetes. We got that transparency. So if you want to look at the specific machine or at the machine deployment or at cluster using the Kube-native way with the kubectl, you got it. And we have no control plane nodes no more, so there's no extra cost for us for managing control plane nodes. And I guess that's it. Thank you for your attention, and feel free to contact me if you have any questions.